Hello everyone. Today we will discuss on the topic three-phase AC circuit. This concept is divided into three parts. Today we will discuss part 1. Topics to be covered: three-phase star connection, relationship between line and phase quantities, numerical. The circuit diagram is that of a three-phase star connected system. It has three windings: winding 1, winding 2, winding 3, respectively for R phase, Y phase and B phase. If the starting end or the finishing end of the windings are connected together, it forms a star connection. The remaining ends are taken out, connected to R line, another winding is connected to Y line, and another winding is connected to B line. So we have R, Y, B, three lines. Basically, in three-phase system, we are talking about line voltage, line current, phase voltage, phase current. We'll see one by one. Now, first, what is the line voltage? The voltage measured between the lines is called as line voltage. Now, we have line R and line Y. So, between these two lines, we have the voltage, or we're measuring the voltage VRY. So, I'm denoting V suffix RY. Between Y and B, we have voltage VYB. And between B and R, we have the voltage VBR. So, we will mention this as line voltages. So, the line voltages are VRY, VYB and VBR. So, next we'll see what is the phase voltage. Now, voltage measured between a line and the common point, which is called as a neutral, is called as a phase voltage. So, we have the phase voltage VR and Vy, that is measured between Y and the neutral, and Vb, which is measured between B and the neutral. So we have three phase voltages: VR, Vy, Vb. So phase voltages are given VR, Vy, Vb. So you are known now how to find out line voltage and how to find out phase voltage. Next, we'll move on to other two concepts. What is the line current? The current which flows through the line is called as a line current. Now we have here RYB lines. So R is the line current to the R line. IY is the current to Y line. IB is the current to B line. So we have three line currents: IR, IY, IB. Now, what is the phase current? The current which flows through the winding is called as the phase current. So for the R winding, we have current I, Rn. Just to differentiate the current line and phase, I am using the suffix N. Similarly, for the Y winding, we have the current IYN. For the B winding, we have the current IBN. So we'll mention all the phase current. Phase currents are IRN, IYN, IBN. So you have studied four quantities: line current, line voltage, phase current, phase voltage. Next, the important concept of three-phase star connected system is a phasor diagram. How to draw the phasor diagram? Now, the phasor diagram are drawn for the phase quantity. So I'll tell you how to draw this phasor diagram. So first, we have to draw the line reference, which is called as VR. Okay, VR I have taken vertically, you can take horizontally. The phase difference between two lines is normally a 120 degree. So another line will be 120 degree with the first line. So this angle can denote your R, VR, this is Vy, this angle is 120 degree. So another vector will come 120 degree lagging from the second vector. So you can compare here, VR is this vertical line, Vy is this, Vb is this. So R, Y, B. Now what is the small IR? That is nothing but the current which lags the respective phase. Okay, so we'll discuss this later on. Just it is lagging current, you have to plot after the vector. So this is the current vector lagging, another current vector lagging, another current vector lagging. Okay, so this is about the a phasor diagram, just how to represent the three phase voltages VR, VY, VB. Okay, next. We have to derive the relationship between line and phase quantities for star connected system. Now the same figure I have redrawn again by showing all the quantities, the line voltage VRY, VYB, VBR, and the line currents IR, IY, IB, the phase voltage VR, VY, VB, phase current IRN, IYN, IBN. Okay, now what you're observing from the diagram, you can see the current IRN which flows to the winding is same as the current IR. Similarly, the current IYN which flows to the winding is same as current IY. The current IBN which flows to the B winding is similar as IB. So we can conclude that in case of star system, line current is equal to phase current. This is very important proof for the star connected system. Line current is equal to phase current. Now, this is a complete phasor diagram for star connected system to derive the relationship between line voltage and the phase voltage. Now, how will we get this diagram? Now, to get, we know VR, we know VY, we know VB. Now we have to get VRY. Now the relation between VRY, which is a line voltage, is equal to VR minus VY. It means these are the phase. So when I subtract vector VR minus VI, I'll get VRY. Similarly, VYB is VY minus VB and VBR is equal to VB minus VR. Now we'll draw the vector diagram by taking the line VR, which is vertically upward vector, then VY, that is lagging VR by 120 degree, then VB, which again lags the second vector by 120 degree. Now, these are the vectors VR, VR, VY, VB. Now, how to draw the line vector? So for that, we have to initially, we will mark the text here. This refers to your VR and this is VY and this is VB. Okay, now to draw VR in the opposite direction, so this is nothing but your vector minus Vy. So it is minus Vy vector, minus Vy vector. Now to get the resultant of R and Y, complete this parallelogram. Now the resultant of but the line voltage VRY, so we can mark here the line voltage VRY. Similarly, you can complete for YB. Y is here, so project B in the other direction. So it is YB. So B you are projected. So complete the parallelogram. So it will be this with this. So resultant will be your vector, which is nothing but EYB. So similarly, you can plot for other diagram, other voltage vector. Okay, so line voltage we obtained from the phase voltage. Now consider this parallelogram. I had to derive the relationship between VR and VY. So I have taken separately this parallelogram. I had taken the triangle AOB. I have taken triangle AOB such a way that this OB is equal to BVRY. So when I take the triangle AOB, you write down what is cos 30. Cos 30 is OB divided by OA. Now what is OB? OB is nothing but half of VRY. So I can write VRY by 2 and OA is nothing but VR vector. And cos 30 is root 3 by 2. You simplify, you will get this relation. Line is equal to root 3 phase. So line current is equal to phase current. Line voltage is root 3 phase voltage. Now power consumed by three-phase star connected load is nothing but 3 times power consumed by each phase or 3 times power per phase. Now what is the power per phase? V phase, I phase, cos phi. Now V phase is nothing but VL by root 3. I phase is IL cos phi. So when you simplify, we'll get P is equal to root 3 VL IL cos phi.
Now, we will look into the first problem. A balanced star connected load of 8 plus J6 ohm per phase is connected to a balanced 3-phase 400 volt supply. Find the line current, power factor and the power supplied to the load. The solution is given the phase impedance ZPH is equal to 8 plus J6. The line voltage VL is 400 volt. So we have to find out now the line current, power factor and power taken by the load. So to begin with, for star connected system, we know that line voltage is root 3 times phase voltage. So first we will find out the phase voltage, which is equal to line divided by root 3. So we will substitute line value is 400 divided by root 3, which gives around 231 volt. The phase voltage VPH is equal to phase current IPH into phase impedance ZPH. Now, we can calculate the current by using this relationship, and here VPH and ZPH is known. We will substitute VPH is 231 and ZPH we will calculate. ZPH is equal to given 8 plus J6, so we can calculate this is equal to 8 square plus 6 square, which is equal to 10 ohm. Now we substitute that here, we will get 23.1 ampere. Once these values are known, next we will find out the power factor cos phi. Cos phi is equal to R by Z. Now what is R? Normally, if we see here ZPH 8 plus J6, it is in the form of R plus JX. Okay, so R corresponds to 8 ohm and Z corresponds to, which is Z phase, corresponds to 10 ohm. So you just substitute here R is equal to 8, Z is equal to 10, okay, which is equal to 0.8 power factor. Power taken by the load P is equal to root 3 VL IL into cos phi. Substituting all the values, we get root 3 into the line voltage is 231 and the line current we have to calculate. Since it is a star connected system, our line current is equal to phase current, which is equal to 23.1 amps. So substitute this 23.1 into power factor, we got it as 0.8. When you simplify this, we will get watt, or it is 12.8 kilowatt. The second problem, three equal impedances each having a resistance of 25 ohm and reactance of 40 ohm are connected in star to a 400 volt 3-phase 50 Hz supply. Calculate the line current, power factor and the power consumed by the load. The solution is resistance per phase, that is RPH is equal to 25 ohm. Reactance per phase, that is XPH is equal to 40 ohm. Voltage given, that is line voltage, is 400 volt. We have to find out the line current, which is IL, then power factor, that is cos phi, and power consumed, that is capital P. Now we will draw the circuit diagram for star connected load. So this is the given value of R, 25 ohm, and this is the reactance, 40 ohm. Similarly, 25 ohm, 40 ohm, 25 ohm and 40 ohm. And the line voltage is nothing but the 400 volt which is seen between these two lines. Now, first we will find out the impedance of the circuit, that is ZPH, which is equal to square root of RPH square plus the reactance XL square or XPH square. We will substitute the values of R, that is 25 square plus 40 square, we will get 47.17 ohm. For star connected system, the relation between line and phase voltage is VL is equal to root 3 VPH. So we will find out the phase voltage is equal to line divided by root 3. You substitute VL, which is given 400, divided by root 3, which is equal to 231 volt. Now, using this relationship, you can find out the phase current, that is V phase is equal to I phase into Z phase. So V phase is known, Z phase is known. You can find out the phase current I phase is V phase divided by Z phase. Now substitute V phase, which is equal to 231 volt. Z phase is 47.17. We will get the current as 4.9 amps. Now for star connected system, our line current is equal to phase current. So we can write IL is equal to IPH, which is equal to 4.9 amp. Power factor, which is cos phi, is equal to R phase divided by Z phase. So R phase is given as 25 ohm divided by Z phase is 47.17, which is equal to 0.5 lag. It is lag because the reactance is inductive reactance, so it is lagging. Now, power consumed by the load, P is equal to root 3 VL IL cos phi. Now substitute all the values. Root 3 VL is 400, IL is 4.9 and power factor is 0.5. The substitute will get power as 1800 watt, or it is 1.8 kilowatt. The third problem, 3 coils each having a resistance of 10 ohm and inductance of 0.02 Henry are connected in star across 400 volt 3-phase 50 Hz supply. Calculate the line current and the power consumed by the load. The solution is resistance per phase 10 ohm, inductance per phase 0.02 Henry, which is connected across the line. So VL is 440 volt, frequency is 50 Hertz. So we have to calculate now line current and power consumed by the load. Now, it's a star connected load. we can represent any star connected load like this.
Hello.
Here we are giving 440 volt between two lines. This is nothing but our 10 ohm resistance, and this is 0.02 Henry reactance for all. Now, first thing we have to find out the reactance per phase X, which is equal to 2 pi FL. So it is 2 pi into frequency is 50. L is nothing but per phase inductance. It is 0.02, which will get it as 6.28 ohm. Now once these things are known, we can go for ZPH, which is equal to root of R square plus XPH square. You can write XP, RPH. So now we substitute the value of R, which is 10 ohm, XPH 6.28 square, sorry, here square. In simplify, you'll get 11.8 ohm. Now, for a star connected system, we know VL is root 3 VPH. So, from the line value, you can find out phase. V phase is equal to V line by root 3, which will get it as 440 divided by root 3, which is equal to 254 volt. Now, once VPH and ZPH is known, we can make use of the relation VPH is equal to ZPH into IPH. So, you can find out the phase current IPH is equal to VPH by ZPH. So, when you substitute, you will get 254 divided by 11.8, which is equal to 21.5 amps. Now, since it is a star connected system, I can write IL is equal to IPH, which is equal to 21.5 amps. Now, the problem is to find out the power consumed by the load, for which you have to find out first power factor of the circuit. So, cos phi is equal to R divided by Z. You substitute R is 10 divided by Z is equal to, we get it as 11.8. So when you simplify, the power factor will be 0.85. So finally, power taken by the load is root 3 VL IL cos phi. Substitute all, you will get 13,927 watt. Problem 4. A balanced three-phase star-connected load of 150 kilowatt takes a lagging current of 100 amps with a line voltage of 1100 volt at 50 Hz. Find the resistance and inductance of the load per phase. The solution is a three-phase star-connected system. Power taken by the load P is equal to 150 kilowatt. It takes a line current of 100 amps and the line voltage given is 1100 volt at a frequency of 50 Hz. We have to find out the resistance RPH and inductance LPH. So to begin with, we'll make use of the formula P is equal to root 3 VL IL cos phi. So we'll substitute all. P is given, voltage is given, IL is given, cos phi is unknown. So first we will find out the power factor cos phi is equal to P divided by root 3 VL IL. Now substitute all. It is 150 kilowatt divided by root 3 into VL is 1100 volt into IL is 100 amps, which gives to 0.787. Now, for star connection, VL is root 3 times V phase. So, V phase is equal to VL divided by root 3. Now, VL is equal to 1100 divided by root 3. So, the phase voltage is 635.08 volt. Now, for star connected system, the phase current is the line current. Now in the problem, the current is given as 100 amps. So IPH is equal to 100 amps. Now directly we can find out ZPH is equal to VPH divided by IPH, which is equal to 635.08 divided by IPH 100, which is equal to 6.35 ohm. Now we know power factor cos phi is equal to 0.787. So to find out the phase angle phi, it is cos inverse of 0.787. You will get the angle as 38 degree. Using this information, you can find out the circuit component R phase. R is equal to ZPH into cos phi, which is equal to ZPH we calculated as 6.35 into cos phi is 0.787. So the resistance value you'll get it as 5 ohm. Next, the reactance XPH is given by 6.35 into sine of phi is equal to 38 degree, which will you get it as 3.92 ohm. Now it is asked to find out the inductance. We know the inductance X is equal to 2 pi f L. So L is equal to XPH divided by 2 pi f. Now you substitute XPH is 3.92 divided by 2 pi into 50. You will get it as 0.012 Henry. So we got the circuit element XL. Then from that we have to find out L. Here L is nothing but inductance per phase.